Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so I'm going to talk about improved mixing time bounds for the L reversal chain in Thorpe Shuffle. And this will be a two-part talk. So today I'm going to I'm going to prove a general theorem about card shuffling. And then in the part two, I'm going to talk about how to apply that theorem to the two shuffles that are in the title. Okay, so some setup. Let PTXY be transition probabilities for a Markov chain. And we're going to be studying card shuffles so that the distribution at time t will converge to the uniform distribution as t goes to infinity. And we're interested in how fast. So I'll quantify that using the mixing time, which I define as the smallest t such that the total variation distance from uniform is at most a quarter at time t. So I'll be interested in two specific card shuffles, which I'll talk about now. The first one is, it was introduced by Durrett as a model for evolution of a genome. And you have n cards that are arrayed in a circle, and each step you choose an interval of cards of length at most L and reverse it. So here's one step of the L reversal chain where the 3, 4, 5 becomes 5, 4, 3. So there are two parameters, n, the number of cards, and L, which is the maximum length of an interval that can be reversed. And Durrett has this conjecture that the mixing time is, it's this funny expression, the maximum of n and n cubed over L cubed times log n. So I'll say some more in part two where this comes from, and I'll just say now that this is kind of a hard example because for this particular Markov chain, the L2 mixing time. So if we define the mixing time in terms of not using total variation distance or L1 distance, but using L2 distance, then in fact the conjecture would not be true. It's a fractional power of n higher. So it's kind of, the conjecture is barely true.
He proved the lower bound.
Right. He proved the lower bound and left the upper bound open. Okay, and the second example that I'm going to be interested in is what's called the Thorpe Shuffle. Oops. Oh, yeah. So in the Thorpe Shuffle, in a step of the Thorpe Shuffle, you divide the deck in two equal piles, and then you line up the cards in pairs. And for each pair of cards, you flip a coin. And if the coin lands heads, you drop from the left and then from the right. If the coin lands tails, you drop from the right and then from the left. And you do this independently for each pair of cards that gets lined up together. Okay, so here it was an open problem to show that the mixing time was a polynomial function of the log of the number of cards. So actually, I had proved that when n is a power of 2, there's a polylog mixing time, but it was still open to show for arbitrary even n that there's a polylog mixing time. Oops. Okay, so the theorem that I'll prove today will give new bounds for the L reversal chain and the Thorpe Shuffle. So for the L reversal chain, previously the best bound for the mixing time was constant times n cubed over L squared log n, which can be a fractional power of n times the conjecture. But using the theorem, I can get the conjecture to within a logarithmic factor. And I want to point out that the spectral gap was determined to within constant factors by Cancrini, Caputo, and Martinelli. For the L reversal. That was for the L reversal chain. Okay, now for the Thorpe Shuffle, previously the best bound had been log n to the 29th, and as I said, that was only for n a power of 2. This was by Montenegro and Titali. Now, using the theorem, we can improve this to log n to the 4th, and for arbitrary even n. Okay. So I'll say a little bit more about these examples in Thursday's talk. No. The only lower bound I know is log n. So there's a trivial lower bound of log n, but some people believe it's log n squared. Okay, let me just introduce my notation. So I'll represent an ordering of cards using a permutation. So if the ordering is if it's 4, 3, 1, 2, then I'll represent that by the permutation such that mu of 4 equals 1, mu of 3 equals 2, and so on.
The inverse of mu. Yeah.
I'm a maverick. That's the big word. So then I can, like if I write mu times pi 1 times pi 2, I'm going to use this arrow notation where I'll draw an arrow from 2 to 1 if the card in position 2 gets sent to position 1, so that I can just follow the trajectory of a card by saying, well, so suppose the initial ordering is mu, and I want to follow the card with the label 3, I can just follow the arrows and see what happens to it. Okay. Okay, so the general kind of card shuffle that I'm going to be studying will be a generalization of 3-card Monte. So in 3-card Monte, there's a table, and the cards are laid face down on the table, and the dealer will move the cards around, and occasionally he'll put 2 cards together and separate them quickly so that you can't tell which is which. So I'm going to model that move mathematically using what I call a collision, which is so a collision is a random permutation that's with probability a half is a transposition, and with probability a half is the identity. Okay, so you can define the Thorpe Shuffle naturally using collisions. So in the Thorpe Shuffle, you cut the deck into 2 equal piles, and then the cards that get paired with each other collide. The L reversal chain, it's not it's not defined. The way I defined it before wasn't in terms of collisions, but there is a way to define it in terms of collisions, as follows. Suppose that I told you that that in a particular step of the Euler reversal chain, either this interval of length k was reversed, or the interval of length k plus 2 that includes this interval plus one card on each side is reversed. Then you could generate the conditional distribution after one step by first reversing the inner interval and then switching the outer two cards with probability a half. Okay, so so we're going to try to show that after a bunch of shuffles, the distribution is close to uniform, and the key operation in these card shuffles is a collision. So it's helpful to what we want to do is we want to analyze how a collision brings a random permutation closer to uniform. And it turns out that a good measure of distance from uniform to do this is so-called relative entropy. So for a probability distribution pi, define the relative entropy as the sum over I pi log mpi. So another way to say that is if random variable x is chosen according to p, then the relative entropy is the expected value of the log of m times the probability of x. Okay, so what's nice about the relative entropy is that you can decompose it into contributions from the different positions. So let's suppose we generated our random permutation by first putting down the bottom card, and then the next from the bottom card, and then the next one, and so on. Now, when we're generating a particular the card in a particular position, we're choosing from a probability distribution on what's the card that will go here, and if we let ek be the expected entropy of the distribution of the card that goes in location k, given what's below it, then we can write the overall entropy as the sum of the ek. Is this okay? So now we can talk about so we have the overall entropy, and we can talk about how much of the entropy is attributable to this position or that position or this block of positions. So okay, so the setup is we have this pi, which is our random permutation. So this is pi is pi is like a shuffle, and so we have pi 1, pi 2 up to pi k is a product of k independent copies of pi. This is like the distribution of the deck after k shuffles, and the relative entropy will be converging to 0, and it's going to be non-increasing. So for any card shuffle, after you do one step, the relative entropy is going to be less than or equal to what it was when you started. And so the way we're going to show convergence is to show that there's a guaranteed loss in entropy every time we do a shuffle. So we're going to try to lower bound the entropy loss using one of these shuffles that involve collisions. There's some formula that connects entropy to total variation. No, I'll show you exactly where I lose the log. Okay, so all right, so we're talking about relative entropy. Now, I'm going to use the fact that the function f of x equals x log mx is strictly convex. And what this means is that if you have two numbers p and q, then the average of f of p and f of q is bigger than f of the average of p and q. So we can define the distance between p and q as this difference. So the difference between the average of f and f of the average. Okay, that was for p and q numbers. If p and q are probability distributions, define the distance between p and q as the sum over I of d pi qi. Okay. Excuse me?
This is actually
I doubt it. I put distance in quotation marks because I'm not. I don't care whether it satisfies the triangle inequality or anything like that. So the distance between probability distributions is the sum of d pi qi. Now, since the entropy is the sum of f over all the probabilities, the distance between two probability distributions is the difference between the average of the entropies and the entropy of the average. Okay, so some useful facts that I will use later on. This function d is, so dpq is convex in q. And then I'm going to use what I call the projection lemma, which is if you have little p and little q, which are distributions of random variables x and y, respectively, then suppose you're looking at the distribution of g of x and g of y for some function g. This can only decrease the distance between the distributions. So the distance between little p and little q is at least the distance between big P and big Q. So in other words, applying a function, when you apply a function, you lose information. So you're going to tend to bring the two distributions closer together. Okay, so another fact I use is a comparison between this d distance and relative entropy. So relative entropy is a notion of a distance from the uniform distribution. dpu is another notion of distance from the uniform distribution. So there's a lemma that relates the two. It says that dpu is at least a constant over log n times the relative entropy of p. Okay, so it turns out that the worst case is a point mass, where it's constant for the d distance and log n for the entropy.
Now n is the probability distribution.
Oh, it was n before, wasn't it? Yeah, sorry, thanks. Every time I give this talk, there's a new issue.
Always make sure your audience has a shorter memory.
Can I get everything on one page? Okay, so I'll use this. Okay, so I'm going to write Cij for a collision between I and j. And I'm going to use the abusive notation. Cij equals a half times the identity plus a half times transposition of I and j. Now, okay, so the key thing to look at in these shuffles is what is the effect of a collision on the relative entropy. So let's suppose we start with a random permutation mu, and so we fix a position j. Now we're going to collide j with some value of I where I is less than or equal to j. So I think of position j as being j from the top of the deck. So what I'm saying is you start with, so you choose a position j, and then you collide that with some position higher in the deck. Now what we're interested in, what is the loss of entropy when we do this? So well, the entropy of mu is the same as the entropy of mu times the transposition of I and j, because well, this is a deterministic permutation, so we're just up to a difference in the ordering, it's the same permutation. Okay, and mu times collision of I and j is has a distribution which is an even mixture of distribution of mu and the distribution of mu times transposition of I and j. So the loss in entropy is exactly the distance between mu and mu times transposition of I and j. Okay, by the definition of this d function. So what is the loss of entropy when you collide position j with position I? It's exactly the distance between the distribution of mu and the distribution of mu ij. Okay, now there's a lemma which says that on the average, so when you average over all positions higher in the deck than j, the loss in entropy is roughly a constant times ej. Ej is the portion of, excuse me? Ej is the portion of the overall entropy that is attributable to position j.
Isn't that conditioned on whatever you see, or do you take the average of what you see first j minus 1 occasion?
So the definition of the entropy attributable to position j is, so here's position j. So let's say, I'm going to start generating my random permutation starting from the bottom. Let's say it's 8, and then 6, and then 3. Now there's something, I'm going to put a card in position j with some distribution.
Eventually you average over 3, 6, and 8. Okay.
Yeah, you average over that, right? Because the entropy of this distribution is a random variable because it depends on the 3, 6, and 8. So Ej is the expected value of this. Ej is expected value of the entropy of question mark given the stuff below. Okay. Okay. Is that okay? So that's pretty clear. So, okay. All right. So I can actually prove this lemma. It's pretty simple. So, well, let me just prove it in the special case where j is n. Okay. So in the case where, so let's say we collide the the bottom card with some position higher in the deck, chosen randomly. Then then the loss in entropy is at least, well, roughly a constant times the entropy attributable to position n on the average. averaging over all I. Okay, so let's say n equals 4. Then suppose if you have a random permutation mu, this induces probability distributions on single cards. So the columns, so here in this table, the columns are the probability distributions on the various cards, and the rows are probability distributions on the various locations. So if you look at location 4, this is saying, well, with probability 1/2, you'll find a 1 there, and with probability 1/2, you'll find a 4 there. So what happens when you take mu and then you do a collision of, say, 4 and 2? So mu times 4 and 2. Well, the loss in entropy is going to be the distance between mu and mu times 4, 2. Okay, but by the projection lemma, the distance between mu and mu times 4, 2 is at least the distance between the induced distributions on the bottom card. So if we ignore all the information other than what's in the bottom card, that gives us a lower bound on the distance between the two distributions. Okay, so what is the induced distribution of the bottom card? Well, if mu, the distribution of the bottom card in mu is with probability 1/2 it's 1, and with probability 1/2 it's 4. In mu times 4, 2, it's with probability 1/2 2, and with probability 1/2 3. So the distance between those two things is the distance between 1/2 0 0 1/2 and 0 1/2 1/2 0, which is just 4 times the distance between 0 and 1/2. So when we take an average over all I of the distance between row 4 and row I, by convexity, this is at least the distance between row 4 and the average over all rows. But the average over all rows is just the uniform distribution. So this is the distance between row 4 and the uniform distribution. And then by the lemma that I mentioned, this is at least roughly a constant times the relative entropy of the bottom position, which is E4. Okay, so that's a proof in the special case where we're looking at the bottom card, but the general proof is much the same. Okay, so that was the case where so what I'm saying is kind of the general lesson of all this stuff is that if you have a random permutation and then you decompose the entropy according to position, and you get say 1 1 10 2 3 or something, then a good way to do a shuffle would be to choose the position with that's contributing the highest relative entropy, and then do a collision between that position and something higher in the deck. Okay. So I talked about the case where the position, so that this is J, then the I said, well, if I is uniform over everything higher, then you get something good. It turns out that you only need I to be roughly uniform over what's higher. So let me define a notion of roughly uniform. I'll say that a random variable x is lambda uniform over 1, 2, 3 up to j if the probability that x equals I is at least lambda over j for k equals 1, 2, 3 up to j. So if lambda equals 1, this would just be uniform, but we're allowing it to be somewhat less than uniform as specified by the number lambda. So there's a lemma which is proved much the same as what you've seen, which says that if x is lambda uniform over 1, 2, 3 up to j, then the expected distance between mu and mu times transposition of j and x is roughly a constant times the interval attributable to j. Okay, so if we were to choose a position I,
Can you write down the definition of J?
it's right there.
Okay, good. Say so.
Entropy of, well, I'll write a more mathematical. Okay, so it's EJ is, so it's expected entropy of, I forget what I'm using for permutations, pi or mu or something. Let's say mu. Entropy of mu inverse of j given mu inverse of j plus 1 up to n.
In this whole discussion, you do not know this will be the rule. This is just how this collision affects given the entropy distribution. Right? You use a random distribution, and you do not know the distribution.
What I'm doing is I'm saying for any distribution mu, so I'm proving inequalities about.
So their mu is distribution, their mu is a permutation.
No, mu is a permutation everywhere.
Distribution is permutation.
Well, it's a permutation, but I'm using when I write entropy of a random variable, I'm using the random variable as shorthand for its distribution.
Use a random.
Use a random permutation. So what I mean here is the entropy of the conditional distribution of mu inverse of j, or the conditional distribution of what card you put in position j, given what cards you put below position j.
I'm struggling with something here. Suppose mu was a completely uniform random permutation.
Okay.
Then mu jx would also.
Right. Then EJ would be 0 because everything's uniform. Because it's relative entropy. Right, it's just it's this unfortunate thing that entropy and relative entropy, like it's like the minus of entropy in the usual sense of the word entropy. Okay. So the upshot is just a general philosophy is that if you you choose a position that's contributing a lot of entropy, collide it with a card that's with a position that's where the position is roughly uniform over what's higher, you're going to reduce the relative entropy by a lot, roughly a constant times whatever this was contributing. Okay. Wow. Okay. Okay. Oh wow, I can't even do my trick of covering up here. So So the general philosophy is, okay, you have this position contributing a lot of entropy, you collide it with something higher in the deck, this gives you a nice loss of entropy. Now, in the shuffles that I've been discussing, there are only local moves. So in one step, you're not colliding a card with something that's going to be roughly uniform over everything that's higher. So what you have to do is you have to look at a bunch of moves. So let's say it's this picture. We have this position J that's contributing a lot of entropy. What we want to do is we want to say look at 1,000 moves into the future and pay attention to what this card is. So let's say we do 1,000 shuffles. Then if in that case the distribution of what this card collides with is roughly uniform over what was higher in the deck when we started, then we're still going to get this nice loss in relative entropy. Okay, so here's how the theorem goes. So the theorem says let T be a random variable less than or equal to little t. So this big T is going to be like how many shuffles we're going to do before we pay attention to the next collision. So for each card I, we're going to say that the match of I equals J. If J is the first card to collide with I after time t, and vice versa. So we do T shuffles, and then after this we start watching the shuffling and we start matching cards up with each other. So we do T shuffles, and then the next two cards that collide are matched with each other, and then the next two cards that collide are matched with each other unless one of them has already been matched with something else, and so on. Okay, and if a card never matches with anything, we say it's matched with itself. Okay. Now suppose that for every k, the random variable m of k is lambda k uniform over 1, 2, 3 up to k. Okay, so every card k is matched with something that's roughly uniform over the cards above it, where roughly is quantified with this number lambda k. Then for every permutation mu, the loss in entropy, when you multiply by pi 1, pi 2 up to pi t, is at least the sum over k times lambda k over log n times the entropy attributable to position k.
You're always assuming that the card is transposed, is collided with something that's higher in the deck?
No, the definition of the match is just the next card that it collides with after time t. So that could be, if 3 and 7 collide, then the match of 3 is 7 and the match of 7 is 3. And for only one of those two will it have collided with something higher in the deck.
Right, but here you're assuming that it's lambda k uniform over 1 to k. Does that mean that...
It does not... Okay, that's a good point. When I say that a distribution is lambda k uniform over 1, 2, 3 up to k, I don't require that the distribution be concentrated on 1, 2, 3 up to k.
But if k is small, then it means that these are getting a lot of... These are getting constant fraction of the mass, total.
Well, it hasn't said what lambda k is.
Right, but in order for us to be getting something good out of it, it's going to have to be right. So in particular, when it's small, we're not going to. This value of t is going to have to be small. right? The value of t is tuned according to which positions are contributing the most entropy. If say the entropy is, say it was this, I'm jumping ahead because I'm talking about how to use the theorem. But if it was all zeros and say, 5, 5, then we would want this position, the match of this to be roughly uniform over what's above it. So we would only want to do a small number of shuffles. Whereas if we were trying to get if we had a 5 down here, and these were zeros, then this guy would have to be almost uniform. So we'd have to do a bunch of shuffles. Okay, but that's how to use the theorem. Right now, I'm just talking about the theorem. Okay.
You're giving us a long sequence of little lemmas. It's hard to focus on where you're going. We'll try.
Okay. Well, yeah. So it's actually okay. The level of complexity of the talk. It's in today. It's like this. And then, but in the next one, it's like this. So I don't want to scare everybody. I hope people come back for Thursday because things get better.
The problem is not the complexity; it's about the motivation of the steps.
Okay.
Why didn't you tell us how you use it then? Or is that the next step?
That's going to be on Thursday. Right. I'm gonna.
Too much. You went off on Thursday.
I mean, yeah. I just want to get to the proof of this, and then I'll get to the. Okay.
Have the cookies and everything after the talk.
Actually, a
Wait,
continuous
can
speed.
you go back to the statement of the theorem?
Yes. Okay.
So could you at least tell us what will it mean? You will choose these lambda k's, right?
I will. Pardon?
No, I agree that this is for every lambda k, but what do you like? What kind of value should I think about lambda k's?
Constant.
For all k.
Well, it's going to be constant for the region. So what we want to do is we're going to have this decomposition of relative entropy, and so let me draw it as a graph. So let's say here's position 1, 2, 3 up to n, and there's going to be some. Say that the relative entroppies are contributed in this according to this graph. Then we're going to want to choose our t. This random variable t is what we have control over. We're going to choose our random variable t such that the lambdas in this fat part of the distribution are big. So we want to the lambdas also to roughly, we want to sort of have big lambdas in here. If there's a bump in the relative entropies there.
Should we think of will you apply this with mu, which is like a constant, a delta distribution?
No. Mu is mu is just some arbitrary random permutation.
Well, you start at the identity, right? And then you do a bunch of things and you get some entropy loss, relative entropy loss, like here. Now, wherever you are, that's your new mu. And then you do it again, right?
Right, exactly.
But you
So-
didn't want to reveal it.
Oh, well, okay, right. Russell's right. Mu is the distribution after time t of your... Pardon?
After some not the same
Previous.
case.
Okay, good.
It's a zero knowledge proof.
Okay, I mean, all right. I shall go on.
Everything
I thought I was doing good. I'm
Yeah, you're very clear. Keep going.
Okay, so let me prove the theorem. So let me introduce the notation pi superscript t for the product of pi 1, pi 2 up to pi t. Okay. So think about again in terms of the dealer doing 3-card Monte. He is so he may move the cards around on the table, but the real action happens when he does these collisions. So we want to kind of ignore all this showy stuff that he's doing with his hands and just focus on the collisions. So what we want to observe is that if I and j collide at some point, then so suppose we know that at some point I will collide with j, we could just initially do a collision of I and j, and it doesn't change the distribution. So,
well, it depends what you do with I and other things that you do with I and j.
It doesn't.
Oh, well, yeah. Okay. Right.
so like if I know that the dealer is going to collide these two cards, I can just step in and just do that initially, and it doesn't change the distribution. So, so that means that pi t has the same distribution as the product of ci mi times pi t. So remember, m of I is the card that's matched with I. So if I go in beforehand, and for every I collide it with its match initially.
That was the mi was the first match after some random variable
Right.
Mm-hmm. Mm-hmm. So in particular, we know that at some point, I and m of I will collide. So if I just go in ahead of time and do a collision, I don't change the distribution. Okay. Now, the point is I'm trying to just, what I really want to do is scratch out this pi t and just focus on the product of collisions. Okay.
The pi t on the right is the same pi t as on the left?
In distribution, equal in distribution.
Oh, I see, because it's a 1/2, 1/2.
Yeah.
Okay, so I'm trying to bound the entropy of mu times pi t. That's what this whole thing is about. So this is the entropy of mu times the product of collisions times pi t. Okay. So what I would like to do is just kind of scratch. Kind of loosely, what I want to say is this multiplication by pi t can only help us. So I can just kind of cross it out and end up with mu times this product of collisions. But we have to be careful because pi t depends on this product of collisions because, what is this product of collisions? It's a collision of I and the match of I. And how do you know what the match of I is? It's based on pi t. Okay, but the way we get around that is we condition on what gets matched with what. Okay, so let M be the collection of what gets matched with what. Then if we conditioning on M can only increase the relative entropy. Okay, because the relative by Jensen's inequality, the relative entropy of a weighted average is at most the weighted average of the relative entropies. So let's condition on pi t and m. Okay, so I end up with the same expression as here, only now I'm conditioning on pi t and m. Okay, now since I'm conditioning on pi t, now I can cross out this pi of t because if you condition on something, it's not random anymore. It's just you're just multiplying at the end by a deterministic permutation, so you don't change the entropy. Okay, so I can cross this out. So I have now mu times the product of collisions. Okay, the entropy of that given pi t and mu. But conditional on m, mu and the product of the collisions are independent of pi t. Because the only way that pi t affects the distribution of the product of collisions is that it tells you what gets matched with what. But if we condition on that, then they become independent. So now I can cross out pi t to the right of the conditioning line. So I end up with the expected value of the entropy of mu times this product of collisions given what gets matched with what. Okay, so now I really can just ignore all this stuff that doesn't involve the collisions and ask myself, well, what is the entropy loss when I start with mu and then I multiply by all of these collisions? Okay. Okay, so I have. Okay, so you start with mu, you multiply by all these collisions, the collision of I and its match. So what we're going to do is we're going to let nu k be the product of all collisions where m of I is less than or equal to I and I is less than or equal to k. So this is collisions that where both cards involved are at most k from the top. Okay. So then we can write the entropy of mu times nu n, which is what we're interested in, because mu n is just the whole collection of collisions. The difference between that and the entropy of mu, we write that as a telescoping sum of the differences between entropy of mu times nu k and the entropy of mu times nu k minus 1. Okay, so we want to figure out, well, what is the difference in relative entropy when we go from allowing just stuff at a distance k minus 1 from the top to allowing possibly a distance k from the top. Okay, well, if k is matched with something below k in the deck, then it's not going to be then nu k minus 1 is equal to nu k because nu k only allows stuff within distance k from the deck, so if you have something below, it's not going to be allowed either way. But if the match of k is less than or equal to k, then nu k is equal to nu k minus 1 times this additional match of k and this additional collision of k and its match. So what is the loss in entropy when we take this permutation mu nu k and we multiply it by a collision of k and its match, which remember is roughly uniform over stuff higher in the deck? Well, I'm going to cheat a little bit here, but if nobody notices how I'm cheating, I'm not going to bring it up. Okay. So remember, we had this lemma that says if you start with a permutation, you multiply it by a collision between k and something roughly uniform over higher in the deck, you get a loss in entropy, which is just the contribution of to the entropy of that position. So the loss in entropy when we look at the difference between mu nu k and nu k minus 1 is roughly a constant times the entropy attributable to position k.
Or the measure of mu nu k minus 1.
That was one of the ways in which I cheated. Okay. It's but it's not cheating because the entropy attributable to position k of mu nu k minus 1 is the same as the entropy attributable to position k of mu, because nu k minus 1, remember, this only affects stuff that's within distance k minus 1 from the top of the deck. So we can't tell the difference between these two permutations until, if we're dealing out cards from the bottom of the deck, we can't tell the difference between those two permutations until we get to the top k minus 1. So this ek is the same as the other ek. And there's another way I'm cheating, but I'm not. Since I'm at the end of the talk, it's
Suspicious.
Condition on M. Seems like it is because M
M
goes
is
stuff
the
below
whole
K as
M,
well.
M is the whole series, right?
The whole
M1
range.
to Mn. And so this ek should be also the conditional probability, conditional expectation given M.
given m, right?
It's not the
Given
right.
m. Right. So that's, I guess, the other way I'm cheating is that m. This mu k minus 1. What this has information about the collisions between what gets matched with what. So when we condition on m, we actually affect this. But it turns out that if k is matched, whatever, say k is matched, say k is 10 and it's matched with 2, then we don't. This new k minus 1 does not affect what happens in positions 10 or 2. So when it turns out that when you sit down and do the calculation, it's exactly like it was in that lemma. So I was cheating a little bit, but in terms of, I mean, when you write down what is the distance between mu k minus 1 and mu k minus 1 c k m k, you get an expression that it's exactly the same as what is. You just get a sum over all the different possibilities, the distance between what's in location k and what's in location m of k, which is
Why are you choosing?
What are the other three places?
no, it's just those two things. It's just, this is not exactly I said, so the lemma gives this. It's not exactly a consequence of the lemma, but it's by analysis, and that's analogous to that in the lemma. By a calculation similar to that in the lemma, we get this. But I think it would, if I went through it all, I think it would probably confuse people more than. All right, so let me end this. So let me end this part of the talk, and then on Thursday I'll show how to use the theorem to get the bounds on those two examples, and that's actually kind of not so. That's actually kind of straightforward.
It's so interesting that you get this max of two expressions in the L reversal.
Yeah.
It's very natural to get in the lower bound because there are two different arguments in the lower bound. And to get
Right.
a max in an upper bound. It's strange.
It is. Yeah, it is.
You're supposed to say no. It's clear to you now. You're not supposed to say it's strange.
Well, I mean, I'm going to talk about that on Thursday. So I promise I'll talk about where the max comes from on Thursday.
But you said you were going to point out where you use the log. Lose the log. That's the log there?
Oh, okay. So one of the logs comes from comparing the. So remember, there's this comparison between the d distance from uniform and the relative entropy, and there was a log there. And then in the examples, it turns out in both examples the way to do it is to divide the relative entropy up into these geometrically growing intervals. So it's an interval of constant length, and then double that, and so on. And then to choose the interval of positions that contributes the highest amount of entropy, and then choose your random variable t to, with that interval in mind, make the lambdas high for that interval. So since you're only kind of
T will be completely independent of everything.
t will depend on mu. But anyway, since you're only optimizing for this one interval, which is 1 over log n of, there's going to be log n intervals, and you're only doing something good for one of these intervals, you get another factor of log n there.
So is the L reversal, like, so is this direct conjecture known if L is constant? For L2, for L equals 2,
Yes.
assume that.
Yes.
In fact, it's stable.
And for any constant L also?
Yeah. Well,
And for L close to n, it's known as well.
L that are some power